Okay. 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 Good morning, everyone. I am Jerry, or Jurius. I'm going to present today my thesis, my master's thesis, regarding few-shot feature adaptation for frozen vision or large foundation models, but precisely on frozen vision transformers. And I'm advised by uh, Dr. Simon. So let's begin. First of all, as we all know, deep neural networks achieve state-of-the-art performance on a wide variety of tasks, um, especially in computer vision. And um, they basically demonstrated that deep architectures can learn rich and transferable representations. So a key factor behind this success, I like to think of it, is the availability of massive datasets, such as those that presented over here, which they enabled the training of increasingly expensive models, and they allowed them to capture complex and semantically align features together across very diverse tasks. So the question that I'm going to answer here, or the problem that we're going to solve, is what if we don't have a lot of data available at hand? What can we do then? But before that, I'm going to talk about foundation models, which is the models that we basically research over here. Um, Two main models are Dino and Clip. For those of you that don't know, Dino is a foundation model that was trained on a large amount of data using self-supervised loss and self-distillation. And it really learned to present embeddings in a semantically in a good feature space. It really did represent features accordingly. The other the other model is called CLIP, which learned how to align text and image data together using contrastive loss. So we increase the similarities between the text and the image that are paired together, and we basically push apart the pairs that are not aligned together. So CLIP was trained on pairs of image and text, and they learn to represent features in the same embedding space. So the text embedding space, sorry, the text and the images are well presented in the same space. I just put it over here on the right. Another model like that is called CLAP, which learned to represent the audio and the text. I don't use it here, but this is another foundation model I think is pretty cool. So just to summarize, Dino model is a very powerful vision encoder, and CLIP is used to present text and vision in the same, sorry, text modality and vision modalities. So two different modalities in the same embedding space. Dino doesn't use text at all? No, Dino doesn't use text. Okay, so the main problem that we're tackling over here is called few-shot classification. At first, I'm going to talk about what classical few-shot classification is and what is the setting that we're working on. So what we're basically working here with is a certain task, or often it's called an episode, where we have a limited set of labeled images, and we have a set of unlabeled images. And our task is to use the labeled set to fit a classifier such that we will maximize the accuracy on the unlabeled set. Um, I reference the labeled set as the support set in the task, and the unlabeled set is called the queries set. And a k-shot n-way q-queries settings is basically we have k images from n different classes and q queries from n different classes. So if we look at the image at the bottom, we have 3 shots of a bird, 3 shots of a dog, and 3 shots of a cat. Okay, So this is a it's a three-shot three-way, and uh, it's supposed to be another, if we have one query, it's supposed to be another image of a bird, but we don't have a complete query set over here. And our job is to fit the classifier on the support images such that it will maximize the performance on the queries. Now, a main problem in few-shot classification is, unlike classical deep learning methods or classical deep learning classification methods, where we train a model on a train split and we test the model on unseen samples, few-shot classification is considered to be harder because we basically train the neural network, or we train the model on a certain type of data, but we have to test it on unseen classes and not unseen samples. So at test time, the classes are unknown. The model has never seen such classes. Um, and yeah, so that's basically a much harder problem than basically unseen samples. And a good classifier will need to, sorry, a good model will need to generalize to these unseen classes that it has never seen before during training. And if we fine-tune the model on these types of classes, it will be very expensive, and it may lead to overfitting due to limited data. And well, it actually needs a lot of data, which we don't actually have. So few-shot classification, classic few-shot classification can be, let's say, split into three main families. The classical way, or the classical algorithm to do that, is to take each classification task, and we can fit a classifier, or we can basically learn a new classifier in each task, and we fit this linear classifier on the query set. So this is called baseline, and baseline plus is basically just a different type of classifier, but it's the most straightforward method there is. We take the classifier, we fit it on the support, and or we train it on the support, and we test the queries based on that. We freeze it, and we test the performance on the queries. Another type of learn another type of method is called the meta learning method. An example of that is MAML, where we train an initialization of the model such that at test time it converges in a few gradient steps. We don't need to run it a lot. And what we are trying to, or basically what we use over right now and is used pretty often today, is in the family of metric learning, where we basically all of the comparisons is metric based on distances. And the algorithm that we use today, that we will use today, is called the protonet, or prototypical networks, where, if you can, as you can see on the right hand side of the screen, let's say that we have 5 shots from 3 different classes, okay? And our query sample is the white dot. We have to compute, Protonet basically computes the mean embedding of the whole support set for each class. And based on the distance of the query to those means, we can classify it to whichever class is classified. Okay, so for example, the white dot is classified for the red class, since its near distance classifier is the red embedding C2. Okay, so any questions regarding that? Will happily answer that. Mm.
A baseline might use a pre-trained encoder, right? It's not
Yes.
not that the entire network has to be trained from scratch on the shots, the few shots that you have.
Yeah, so baseline plus and the metric learning methods can be used on pre-trained encoders. Meta learning, I have never tackled a meta learning. Basically, meta learning needs to be trained on some kind of split. But the most important thing is, at test time, the classes were unseen, or basically the test split that we're testing on, the classes have never been seen by the model at training time. Okay, so fine-tuning methods and metric learning can be just like plugged and played on any pre-trained encoder.
But when
Yeah.
it is also trained, is always trained
You can train it based on the loss of the protonet, but it's not mandatory to do so. Okay.
So what's F? F data is always trained on some.
This can be a pre-trained model. It's yeah, on Dino, for example, or any pre-trained CNN. Okay, so um, I'm just gonna say before, usually the few-shot classification datasets, for example, we have mini ImageNet for the vision. It has explicit splits, like certain types of classes for train, certain types of, they're all distinct, like the intersection between the classes in the splits is distinct. It's the empty set.
You
So
always train this on many classes. Then you
um,
use it on the few shots to
I
predict
wouldn't
the.
say many. It's different. It's different. Like before, I think mini ImageNet. I don't know how many classes there are honestly, but I forgot. But we will see in a bit that it still has limited representation. Okay. So what I explained just now is called, I call it as the classic few-shot classification or classic image few-shot classification. Now I'm going to talk about text-based few-shot classification. Over here, we need, of course, since it's text-based, so we need both modalities. We need the image encoder and we need the text encoder. And if you recall, we computed the mean embedding of the support. Over here, we can use simply the text example. Like if you can see here, we have a plane, car, dog, bird, whatever. We can say a photo of this object. We can have n embeddings per, like for each class, there will be an embedding. And we can use those as the anchors or as the prototypes. And then text-based. Yeah, yeah, exactly. So
It
for
should be like one token per class, or it could be like a sentence description.
no, so they for each data set they use a different sentence to embed it.
Sentence,
Yeah.
okay.
So for example, over here you have a photo of an object, okay, and they use the text encoder in order to encode it into an embedding. And so since we have n classes, we have n prototypes. These are the text prototypes. And the classification is basically the cosine similarity between the image embedding and the prototype of the text. Okay, so it's really similar
Not zero shot.
because I will use it in a few-shot setting. But this is basically, this is zero shot, but I will use more few examples later. Okay. Okay.
Oh, it's the same, okay.
Hmm?
It's the same title of the problem.
Yeah. Just a minute. Okay. So few-shot classification is split into two different families. We have an inductive and a transductive families. What we tackle over here is the problem of set input problems, where the input is basically a set of items. You can think of a few-shot classification task as also the support set and the query set union together. And so this is a set of items, okay? And in set input problems, the performance is greatly enhanced if the items are compared within the set together. Like you don't treat each one of them independently. So some examples of this, what I just described is called the transductive few-shot setting. And some examples for is Laplacian shot, PTMap, which is a very powerful algorithm, paddle, and the BPA transform, which I will dive deeper in this presentation. We will research it a bit, and we did enhance on it. Okay. So let's talk about the BPA transform, which is short for the balanced pairwise affinities transform, which is a feature set transform. And basically, it's a representation learning technique. We need, because the name of the game in the few-shot classification task is representation. When we represent the features correctly, then it starts to move, like we start to see progress. Okay? So let's say we have n inputs, that's the whole set. We use a pre-trained feature extractor that has never seen these classes before, like I said before. We embed those into like features, okay? And then the task head, which is a classifier or any other task that you want to use it for, basically gives me the output, okay? This is a very straightforward pipeline. So like we said before, the extractor has limited representation. Okay, so the task head should compare the set items together and not treat each one of those features independently. And if we fine-tune the extractor, that's very expensive. So a nice solution to this is to add a transform before those features. So we can change the representation before the task head. Okay, so a nice example of this is PCA, self-attention, our like the BPA module and our multi-BPA module, which I will present in a bit. And these are contributions. They are threefold or four. We introduced the multi-BPA adapter, which extends large networks, and it's adaptive to feature set inputs. It's a very simple pipeline. It's differentiable, so it can be trained. It's very efficient, and it's equivariant. And we use it to test, we basically test it on classic feature classification and text-based feature classification with various tweaks here and there. We will talk about it in a bit. Okay, and we did rigorous experiments, and which you will see in a bit. So until now, this is basically the setting. Are there any questions regarding the setting?
You described the BPA?
No. Okay.
I don't know if it's important now or later, but in the previous slide, samples are not previous one. X1 to Xn are all the. It's only one. It's the n shots of one class, or it's all the.
No, so the set over here, or basically the set input, you can think about it if it's a k-shot n-way q query setting, then you have k times n plus q times n. And that's your whole n. Okay, maybe it's like small n. Small n is basically k times n plus q times n over here.
Maybe say something about the constructive versus inductive.
Okay. So over here, for example, we took a look at fine-tuning the objective and the protonet objective, and basically how the classification how is the classification done over here? We take the mean embeddings and we take each one of the query embeddings alone, no prior knowledge, or basically it's just the embedding that got extracted from the feature extractor, and we classify it based on that. And over here, I talked about transductive setting. I will dive into it. I will dive deeper a bit later, but basically, there's a lot of information that is not being used, let's say, by the unlabeled set, because we can think of this classification task as two parts. We have the supervised subset and the unlabeled or the unsupervised subset. So we can use the unsupervised subset in a way, but we can't use the labels, of course. We can only use the labels of the supervised subset. So we can model, for example, the distribution of the unlabeled subset, and we can do some comparison using that. So there are, for example, these four algorithms, they utilize this distribution in some way. And of course, this gives powerful, like more powerful representation.
Supervised subset is the
Yeah.
query, right?
The supervised is the support set. The unsupervised is the queries.
So
So we don't know what classes.
Exactly. Yeah.
So you're actually solving two questions in one go.
Why two
Right?
questions?
You want to know the classes, and then you also want to do the query given the classes, or you just want to distribute them into classes?
No, I just want to classify the queries into a simple classification problem. Okay, but in transductive learning, we can utilize the query distribution, for example. Okay, as long as we don't use the labels explicitly, it's legal. You know.
But maybe it's like it's confusing that the inputs are not just a set of images; they're actually the query, the whole query set, and
Mhm.
the
But they're not
And
labeled
the
as
support set.
query, but are they labeled as query and support? Is there a
Yes.
distinction between the two?
Yes,
Yeah.
Yeah.
it also has the attribution to a specific class. So you have 4 images that are class 1, then 4
But you
that are
don't know the
class
labels,
2.
but you don't know.
In the
You know
query
that they
set.
are class 1, you call this class 1. You don't know what class
Mhm.
it is, but you call this class 1. Then you have
So
another
you
one
have
that
the
you call class
clusters?
2.
Yeah.
The clusters are labeled.
Yeah,
It's not a matter of clustering into classes.
Mhm.
Okay, so
And I have a related question, which I think maybe it's the same confusion. Can you, what's the training foundation test separation here? It's like, this is like, I think what is confusing.
well,
Okay.
The
I
query
would
is a
put the
test
in-
kit.
I would just put the input in clusters, right? So I do X1, X2, N, and then you have another X1, X2, Xn, and another X1, X2, N. So there's
You can think about this picture over here as the query set, for example. So we have 2 queries from 4 classes, and this is our end goal to yeah, okay. We can think about, yeah, we can think about this image as the query set only. Okay. So this is our task. We need to cluster together the 2 lions, the 2 cats, the 2 whales, and the 2, I think, goats over here. Okay. We don't classify the support set. We can utilize the support set to fit whatever classifier we want, but this is our main objective.
That's the few shots that are given to you?
Yeah, the labeled, the small labeled set. Yeah.
But they're in this input group or they're separate?
Okay, so in transductive settings, we can union them together and utilize the whole set together. Okay, but in inductive few shot setting, we have no knowledge of the queries whatsoever. We just take the embeddings and classify it based on that. But when we, if we apply one of the algorithms over there that are written down, like Laplacian shot map or BPA, what I'm about to explain now, we have to union the 2 subsets together, the support and the queries, and we model the entire set together, and we change the representation based on the entire set. The features are compared one to another, both support and queries.
I'm a little bit lost, sorry.
I think
Okay.
maybe before the transductive, maybe it's worth describing the few shot learning again.
No, few-
probably.
It's good, but
So you have
any
new-
classes,
new
Sorry,
K new classes
right,
that you've never seen before.
Right.
Each of them has n samples.
but you give them as a class. You
Yes.
give, here's.
And yes,
class
and then
one,
you have a
class
query,
two,
which is a new
one,
image,
you want
and
to map,
you need to map them.
right.
Now it's the
Here-
same problem again. If you want to solve it while you do something, you want to also take into account the query, not solve it separately. So for example, I think we applied before, there's a prototypical network, right? Which maps,
Just a minute.
first
Up.
computes the 3 centers of the 3, of the K equals 3
But now you
clusters,
don't have
and
those
then
clusters.
maps.
But now you don't have the clusters.
Oh, you do have the clusters.
You still have them, but
Kind of, instead of working in a latent space that takes into account everything, you're working in a latent space or looking in a sub part of it that is relevant to the query and the classes. That's the point. So you still get the same, classes.
Yeah, you still get the same classes.
Classes,
Yeah.
and you get a query.
so
No,
in this
it's-
example, the difference would be
Many queries, yes.
No, but this is the difference between the transductive and the other one, right? Like you use the kablanut, like many queries.
yeah.
Mhm.
Yeah, you
Like
use them.
considering-
Use a structure. Use a structure of the queries.
So if you want to compute those 3 centers and then map this Voronoi map, you would compute this. You would use the query samples to compute this.
Hmm.
Then you would send.
Exactly.
The inductive setting is more strict, like you have access only to the support images, the examples. And then you have to come up with some classifier. And then someone gives you one query, you have to classify. The more general setting is the transductive, where you already, from the beginning, you have access to
to the query.
query set, they're not labeled, but you can look at their statistics.
You can utilize the structure or the distribution or something.
The green and
The green,
Okay, so
the green, red, and the blue are support. The query is the yellow dot over
Right.
here.
It's better because there's only
Yeah, white dot. Yeah, but the algorithm over here. Yeah, you can utilize all of the white dots in order to fit a different classifier.
But the assumption is that the number of query points is the same order of magnitude as the n, as the number of sample, or
You
or
have
it can be much
Q.
larger.
No, you have okay. So you have Q queries of each one of the n classes.
I think Q is much larger than that you have for each class, the label number.
Yeah. The support set, you mean?
Is the query number of query samples larger than the number of contexts?
What do you mean by context? So what, yeah, it is. It's much larger. For example, or typically, yeah, typically.
So basically, assume you have a few labeled data and you use a lot of unlabeled data to classify everything.
To help with the classification. Okay, yeah.
Oh.
Or to come up with a stronger method.
Do you Q per each class? I mean, do you rely on the fact that they're only Q? Or that
No,
must be Q?
no. Our method doesn't care how many queries are there from each
Yes,
class.
but can you take advantage of the fact that there are only 3 per set? So if all 10 of them are going to one set,
Mhm.
then you say something's wrong with that.
No, you can't do that.
You don't assume that.
No, you can't do that because that will be illegal. You don't know if you say, like, for example, we have 10 queries per set. Okay, this is an unlabeled data. Like, this is unlabeled data. You can't utilize this fact inside.
It's not necessarily.
So it's not necessarily Q.
Yeah, it's not necessarily true. Exactly. Yeah.
They can all go to one set.
Yeah. Okay. So I'm going to talk about our method, like how we tackle this problem. I will talk about the BPA transform more like in a few slides, but let's just assume that we have knowledge of what BPA is. I will describe it briefly over here. This is our setting. For example, this is also three-way, two queries. So this is our set, okay? Yeah, we have two queries from each class, and we have to classify these two queries. We utilize a vision transformer, a frozen vision transformer. Okay, we don't need to fine tune anything, and we have how much? We have like these embeddings. Okay, how much are there? Let's say I don't see. Yeah, 15 overall. Okay, we have 15 features. So we pass them through the transform, which is a non-learnable transform, to change the representation. So for now, we can think of the BPA transform as a clustering method or a clustering transform, which compares the features one to another and gives me a stronger representation or a stronger clustered representation. We start by computing the pairwise distances of this feature. I don't have the laser, but let's say okay, sure. Oh, yeah. Ah, so one second. لا اوكي صدق لا זה לא פאורפוינט זה keynote אז We can look at the F times F transpose. It starts from there. Okay. So this is the pairwise. Let's say this is a cosine similarity. Okay. When we do 1 minus this cosine similarity, we get cosine distances. So this starts from there. We get the pairwise similarities from the features, and then we add infinity to the diagonal or some large number, and we apply optimal transport on this n by n matrix. Okay, I will briefly talk about what optimal transport is in a couple of slides, but this is a nice algorithm that distributes the features to themselves over here, basically. And then after the optimal transport has finished, we add the identity matrix. And then we have some sort of attention, something that mimics the attention mechanism. Basically, this whole BPA transform mimics the attention mechanism, but especially this times F, which is our features, our input features. We multiply this affinities matrix by the F, and we get the final transform in the main or in the dimensionality of the visual encoder. Okay, so we don't even play with the dimensionality of the features. We project them onto the same dimensionality. And after the BPA transform, we can just do the prototypical task, and this has proven itself to be a better, let's say, a better algorithm for clustering. This has greatly enhanced the prototypical accuracy by itself. So what is our contribution? Since this BPA transform mimics the attention mechanism, we can mimic the transformer with it. What happened? Okay. So we add an MLP, or we call it an adapter over here, but we basically add an adapter and another BPA transform after that. Okay, so our entire pipeline looks like this. We call it the double BPA pipeline. And we can basically think of it as a transformer for a few-shot classification tasks. Okay, and the vision encoder is still frozen, but the MLP adapter is trained, and I will dive deep in what is it trained on just in a bit. So yeah.
Can you describe the full algorithm with respect to S and Q? So this is how you process S and Q together, right? But then you need to classify somehow all the cubes.
Okay, so it's pretty straightforward. We take the S and Q through the visual. Okay, so over here is a great example of how inductive pipelines work. Okay, how do we take the representation of S and Q via the visual encoder? We basically pass each image as a standalone image, and we get an embedding. Then we concatenate those embeddings together, and the BPA utilizes the whole structure of the set. So it changes the representation into the yellow vector, but then the adapter processes each one independently. So it's back to an inductive pipeline. After that, we have the orange, like the process, the MLP processes the features and they transform it to an orange matrix. We concatenate them again, and then the BPA transform processes this again and changes the representation. Okay, and then we have a concatenated, yes, we have the concatenated set. We can just utilize the support embeddings to, like the transformed support embeddings to compute the mean embeddings, and we classify the queries based on those newly transformed supports.
Average all the S examples into K clusters.
Yeah, so for example, S1, S2, S3 gives me the green star. Okay, S4, S5, S6 gives me the blue star, and the like the black dot is a query sample. Okay, and based on the distance, I can just classify it.
So BPA does not take into account the sets.
No,
the
no.
division into sets. It just works on all the group of images that it gets as input.
Yeah, that's an interesting question because we tried a lot playing with that. I can a lot.
So you back propagate through the BPA.
Yes, the BPA itself is Yeah, like you can take the derivative of it and the MLP, of course.
And intuitively, like you don't need it to be double VPA, you can do triple VPA or not.
I will talk about this in a bit. Okay. So yeah, interesting insight. Yes, because if you look at the okay, so F times F transpose plus an identity matrix in the MLP, yes, you project it just like the vision, just like the transformer, the MLP over there takes D, goes up to 4D, and then back to D. We just use the same architecture over here. I will present some ablations on the hidden structure after that, okay? So yeah, you can think of it that the MLP takes this to another like it semantically aligns it in a much greater dimension and then projects us back to the original dimension. Okay, so this is basically the pipeline. If we have this entire set, over here I called it like M images overall. This is our matrix, and now this is the algorithm of the BPA. Okay, so it takes the pairwise self-pairwise distances. Okay, this can be, by the way, this can be any distance matrix that you want. Just cosine seems more stable than Euclidean distances, so we used cosine distance.
It's just that Euclidean and cosine is the same thing.
Yeah, but they're in general take features from any embedding, they're not necessarily normalized.
Okay, so we take the self-pairwise distances and we fill the diagonal with infinity or a large number. Yeah. Yeah.
You can show that the relative between like if you have cosine similarity between A and B and A and C, where A and B is larger, then the distance will be smaller also. But it's not necessary that the same things will apply.
So what?
It's all about.
No, it depends how you normalize.
The point to show you it's the same.
What's the same?
The cosine distance and Euclidean.
No, it depends.
It's
how you
not the
normalize.
same.
Here you normalize maybe everything together, or
No,
each.
don't know each.
Yeah, no, so this is cosine, for you could do it, no,
Or not should know.
Euclidean without normalizing,
Normalization.
that's a different option.
No, but Euclidean cosine,
If they're
if it's
normalized,
normalized
it's
cosine,
equivalent.
Euclidean is the same thing.
Yeah.
Factor two.
Yeah.
Like
Yeah.
one
But
minus
it's
is
possible
factor two.
to do Euclidean
Without,
normalizing.
yes, so this I see why. it's
So the first line can be swapped out for any distance metric of your liking. Okay, it can be cosine Euclidean, or I think there's a new one right now. So no, there's an even more stable metric that came out like a couple of months ago. I read about it. As long as it models distances, it can be swapped out. It's not a problem. And this is called we call this the cost matrix. Okay, so why do we call it the cost matrix? After that, we fill the diagonal with large numbers, and optimal transport, we solve this self-optimal transport type of problem. Okay, so we can think of optimal transport for those that don't know. Okay, I just most of you. Yeah, so over here, the order of the features is this is a three-shot, three-way, two queries. So we have the first 6 rows are the supports, and the
When you
just a
expect the
minute.
clusters, then the Q's, the n sets to be blocks.
This depends on how the order of the you do expect. Yeah, this really depends on how the order of the features is presented in the matrix. Okay, I will showcase another example. I'm not sure over here what the order is, but I have another example later on that I actually know what the order is, so I can show you over here how the clusters are clustered. Okay, but I think over here we have three shot.
over
I'm
there?
not sure. I'm not sure. I will check it out later. Okay, so once we have this cost matrix, we solve this self-optimal transport problem. Okay, so optimal transport, for those who don't know, it basically solves a min cost max flow problem between between like two distributions. So what is the minimum cost of the maximum flow between two different distributions? And over here, we basically spread the flow from the features to themselves. But since we added the big numbers on the diagonal, we force the features to present it, sorry, to transport their flow onto the other features, okay? Because if we don't do that, then I just basically transport all of my costs to myself, okay? So after that, I like to see this transform, like how it does it. So the algorithm to solve optimal transport is called Sinkhorn. It's a very nice paper, and it converges within a small number of iterations. It's linear operations on the matrix itself, and it converges in like 10 to 15 iterations, which on PyTorch is just like that. Okay, and at the end, after we get this optimal transport matrix, we multiply it by the input, and we have this type of attention. You can say, by the way, those don't know, Sinkhorn um, Sinkhorn makes the matrix or transforms the matrix into a doubly stochastic matrix. So unlike softmax, it's a more stable version than softmax. So this can be thought of as the softmax, on the Q times K, whatever, normalized. And then at the end, we multiply it by the input again. Okay.
Weight of the diagonal is 0%?
Okay, yeah, so it's not written here, but after the transport, we add the diagonal, we add the identity matrix. So we present the, like the main diagonal is 1 again. Okay.
Can you say what's the Sinkhorn?
The input of the Sinkhorn is the cost matrix, which is the self-pairwise distances, okay, plus the infinity on or the big number on the diagonal. So after that, just a minute.
It's like you're asking algorithm to move the points from what they are to match the costs.
Exactly. Transport your cost to to all of the other features. Okay.
Right, if the diagonal here is bright and there the diagonal was dark.
Yeah. So
What
just
is one minus?
I will show you over here. I haven't put the line in, but we also add the identity matrix after the optimal transport, if you see over there. Okay. Because once we apply the Sinkhorn, because I had a large number with like the main diagonal had a large number, it's basically 0. So we add like 1 because, I'm similar to myself. And
Isn't it? No, it's like
yeah. It's exactly.
You add
So
to
this can be thought of as a residual connection. Okay. If we untangle this, okay. This plus 1 and then multiply with the input, we get the original dimensionality again, and we can work with that. Okay, so this is our new features. We changed the representation, and these are our new features. Okay, so after that, we forward it through the adapter, okay, and we get another set of features, and then another BPA transform of what I just showed you. Okay, so over here, you can see that the adapter is exactly the same as the transformers. It takes D up to 4D with the same dropout, with the same activation function, and back to D again. Okay, so now this adapter is pre-trained and fine-tuned as well. So I'm gonna talk about that. The thing about adapters is, since it's a small network, it doesn't take a lot of time to train, and it doesn't take a lot of time to fine-tune, and it can be used as a plugin for any other network, okay? So I talked about this in a previous seminar, I think like a year ago, but I utilize this over here as well. So basically from our experiments, we saw that initializing the adapter from a local minimum and not randomly yields much greater results, especially on heavy pre-trained or large encoders. Okay, so a nice, like a good representation, a good data set to train this adapter on is ImageNet. So we use ImageNet, but if you look at the hyperparameters, it's only like 50 epochs and 256 batch size. So it doesn't even go through the entire data set. It's just like you initialize it at a local minimum. And we train it using the standard cross entropy loss, visual encoder features, then adapter and cross entropy. We backpropagate through the cross entropy and using the cross entropy loss, and we train this adapter. Okay, but then since we are working in a few shot setting, our test time classes are different from what we saw. Okay, so we can utilize the power of the support set to fine tune this adapter even more and fit it better on our set. So during the fine tuning process, we backpropagate through the BPA to the adapter. That's why there's a fire sign on it I don't know if anyone noticed, but on the figure itself, there's a fire sign on the adapter. We backpropagate only on the support samples, and this is our loss over here. It's basically the cross entropy on the distances to the prototypes. We backpropagate through the BPA, and train this adapter based on that. Okay, so this fine-tuning objective is, I don't know, it doesn't take time at all. Like you don't even feel it since the network is so small. Okay, yeah.
So the loss so PC is the centers of their class.
PC is the prototype or the mean embeddings of the support set. Yeah.
And when you backprop, you only backprop through F theta, or only because F theta also appears in PC.
No, this is
PC,
F theta. This is
or
it's the entire, basically F
it's
theta.
S.
F theta is the final features over there.
Yeah,
Okay.
they appear twice. They appear also where they are written there, but also inside the computation of PC, which is the mean of several of those.
Oh yeah. They do.
Then you
They do
backprop
appear
through
then.
both of them, or you freeze one of them.
No, I back propagate through all. I don't know if I'd understand the question correctly. I'm not sure, but I will explain it.
S, like they're called S on and they just change by color. So
Yeah, because they transformed.
after the BPA.
Yeah,
After the-
because they transformed. Like the features are not themselves, but they have the same ordering. Okay, so the loss over here, we take this is basically a cross entropy loss over the distances. Okay.
But the thing is that the target of the cross entropy also includes the prediction. So you have like two.
There's no ground truth.
Yes, there is.
Okay. I think I understand what you mean by that. Since we have to only use the labeled set to backpropagate over here, okay? So in some way we compute the loss of the mean embeddings based on only the support set. So we derive only based on the support set. We use the support set to compute the mean, but we also use the support set to compute the distance and backpropagate using that. Okay, so this is like a self-contained loss. Okay.
Then it's like a clustered, it's a measure of the goodness of the clustering, and the clustering is a ground truth in the simplest sense.
Exactly, yeah,
Yeah,
exactly.
but if you compute this loss in PyTorch and then say backwards, then it will compute both losses. So you have to do like a stop gradient on the PC. I don't know if you did it or.
Uh,
We can talk about later.
Okay.
But I had also another question is whether, so when you backup, you have to backup through the, let's say, 10 iterations of BPA?
Just a minute. Regarding your first question, the PC should be changed.
Okay, maybe that. I mean,
Yeah, I like.
Sometimes it's more stable to, whenever your parameter affects both sides of the loss, then you freeze one of them and you.
Okay, yeah, that's interesting. But no, I didn't do it like that. Like I said, the PC should be changed according to the loss. Okay, I didn't freeze the PC. Now I understand your question. Yeah, that's an interesting approach. I don't know. I can try it.
The second question is when you backup, you have to backup through the 10 iterations of the BPA.
Yeah, this is an iterative.
That's stable.
Yeah, that's stable. You also have yeah, that's pretty stable. I mean. Okay.
Also in the original BPA, you have to find.
Yeah, we have an option.
Yeah, in the original work, you can fine-tune the model based on the derivative of the BPA, but then there's a problem over there because let's say that you're evaluating the prototypical algorithm, ProtoNet, and you fine-tuned it on a transductive pipeline. So what the experiment says there is if we fine-tune the model based on a transductive derivative, does that help an inductive pipeline? Because the prototypical itself is still an inductive algorithm, and that did help.
I mean, if you hold out some of the query networks and then you test on those. That's how you test this. Maybe we can
No.
follow up later.
Okay, yeah. But over there in the original work, you had like a special split for the training data. So you compute the loss based on the query ground truths over there. But then at test time, you just use this encoder that you trained or that you fine-tuned just on the test set. Okay, so we can just move on from now, and then we can talk about it. This is basically, we call this the double BPA pipeline because, surprise, surprise, we also did a multi-BPA adapter pipeline. So just like a transformer, we shouldn't have just like two BPA transforms to lead to a single adapter. We can just multiply that. So we can stack the L adapters with L plus 1 BPA transforms. Basically, when L is 0, this is a single BPA transform, and L1 is the double BPA pipeline that I just explained. But yeah, we can do that. I will showcase the results on that in a bit because I still have another problem that I want to discuss. But basically, just I'll give you a preview like of what came up. When we use a not so powerful visual encoder, this helps a lot because we're basically adding or we're adding complexity to the network, with the learned parameters. But when the visual encoder is strong,
לא רוצים את החדר למעלה?
לא שיירתם?
שלנו בעבר, ואז שלנו למעלה, זה היה נראה פנוי.
אבל נכון שרן שתיים, שני חדרים.
אי אפשר? ביקשתי מבליבס.
כן,
זה צריך יותר מארבע דקות.
לא, זו שאלה.
היא אמרה שתבדוק את זה.
Okay. So when we're adding complexity to the network, especially when the visual encoder is, relatively weak, this does help quite a bit. But if the visual encoder itself is very strong, then adding those parameters just becomes too much. And I will show some experiments later on to showcase this. I will when I will show you the screen.
EPA several times, doesn't converge, it doesn't kind of become more.
No, because that's just a bit too much parameters. Yeah. I tried multiple variants of this. So first of all, I tried since the PPA is non-learnable, it's the same transform, but I tried a couple of approaches for this. So the approach that worked best is it's a different adapter for each one. So if it's L times L, so we have L adapters and we train. Hmm? Yeah, different adapters. Also, I don't know if anyone noticed, but this adapter also has the residual connection, like the resonant, okay? Exactly like the transformer. And I also tried doing it using the same adapter. So, it's like circular.
And that doesn't.
No, that doesn't converge. Okay, so moving on now, I will talk about this in a bit, but I'm going to talk about now how we solve the image text like the text-based few shot. There are a couple of things that are interesting over here, and I will talk about it. So we're using clip over here, okay? Because we need the text anchors or the text prototypes, and we need to classify the image based on those text embeddings. But there's a nice, there's a problem in clip. For those of you who don't know, there's a modality gap in the clip embedding space. Okay, so even though that clip is trained to semantically align the image with the relative text, if you can see, as you can see on the right-hand side, there's a big modality gap in the same embedding space. So the text is clustered on one side, and the image embeddings are clustered on the other side. This is known as the double ellipsoid geometry. Okay, so BPA is geometric is based on geometric distances. So a nice intuition for BPA is if me and Naaman are in the same class, then we should see the others in the same way. That's how we cluster each other, like that's how we're clustered to the same class. If we see the rest, if two embedding points see the rest in the same way, then they're likely in the same class. Okay? So what can we do when we have modality gap? We can either play with the distances, multiply it. Like the first thing that comes to mind is that we can multiply it by a factor of some sort. But there's a nice solution to this. It's called orthogonal procrustes, OP. So given representatives of images, it's basically like this. Given two spaces with respective like paired representatives. So over here we have image and text. If we have an n by d representatives from the image and an n by d representatives from the text domain, we can do a transform that is basically a rotation and a scaling. Okay, so it's like a rotation and a scale of a transform, and this can be computed using SVD. So in PyTorch, it's pretty fast. And using SVD, we can learn this, or we can basically compute, it's not learn. We can compute this rotation and scale transform. And in that way, this will, how do you say it? Like save the intra distances between those embeddings as best as possible. Okay, and we need to align those representatives together. So, for example, the first feature from the image should be aligned to the first feature of the text, depending on the pairing. And so we use this in order to solve the modality gap, okay? Before using BPA or after I have.
So what the processes is just maps the two cones, one into the other, or those two each other.
Yeah,
basically, right?
yeah, exactly.
So why did the clip originally do that? I mean, why, so does it work better when you use, if you take the latent space and just do this mapping, does it still work well? Because the distances, the whole point of this clip was that although it's two cones, you still have a shorter distance between the image in one
And
cone
the
to
text.
its text in the
Yeah.
other one.
Exactly.
Right, you still preserve that, but once
Mhm.
you do this mapping,
Mhm.
you still, supposedly you preserve it, because that's what
I
you do.
do preserve it,
So
yeah.
wouldn't it work better after this kind of transfer?
אנחנו נרד ל-107, אז אם יבואו סטודנטים, צריך לארגן את זה.
לא, מהר, תעזבי את החדר הזה שבא.
Why did you say scaling? Because if it's an orthogonal matrix, it has to preserve, it can't scale.
No, it's two. It's supposed to be two matrices.
So you're orthogonal, that means it's בדיוק, scaling. The name orthogonal means that it's I, which is no scaling.
I remember it was two matrices.
But you do normalize that the mean is zero. You have to normalize
Yeah.
the mean is zero. But
כתוב I.
Okay. What was your question?
when I read that stuff, if you do this transformation and they're now closer to each other, supposedly clip should work better.
No, not necessarily. It doesn't seem that intuitive to me.
It's like there are many images that get similar sentences and many sentences that get
Like text.
yeah, like it's a complicated relationship. So it has to balance over the whole thing somehow. When you train it, you do it over batches with the contrasted map.
Mhm.
When you do this and you train it and it performs well, if you look at the result, this is what you have. Like this is the essence of the shit.
For sure. I mean, that's the outcome, but then intuitive. Why doesn't it work better when you bring the matching pairs together?
Because it's training objective.
It's not the goal.
It's not the goal. Yeah.
Just, no, the nearest neighbor has to be.
A class, a text class.
Right, but when you do this,
To be as close as possible.
If
supposedly this brings it even closer.
Hagit, I think your solution should be also like just off the top of my head is to add another type of SynCLR loss or something during the training of the clip objective.
Sorry.
No, yeah, that the task is you have to be closest to the correct label. You don't have to be close to it. You don't have to align it. You just have to be closer to the correct label than you are to any other label. So it's a different objective.
True, but don't you maintain that when you rotate? When you rotate,
We
you
haven't
go to-
checked
wouldn't it
applying
close?
this, but I assume that it won't.
You're saying that
Work.
it
I don't think it will work.
be very close and
Closer, but not necessarily. It's just
not
a.
necessarily closest.
It's a different.
Okay.
For our, for using the BPA, we do have to have
Right.
the line, so that's why.
Okay. So moving on. So now our pipeline looks like this since we have also the text embeddings. So it's a much larger feature matrix. It's basically still an N plus support.
But the text.
It's plus the text embeddings basically.
Yeah.
You're missing a green one that it's the text embedding.
The text went through a different transform.
No, it's the same.
The VLM?
It's the VLM clip.
Oh,
Okay,
What do you
so
It's two different transforms, like it has two heads.
yeah, but it's the same model. I mean, it's
I see.
it's a clip model.
Okay. Which has different dealings with.
Yeah. So the support and the queries go through the vision transformer or the ResNet encoder, and the text embeddings go through the transformer. Okay?
Then BPA you do on everything?
On everything, yeah, on everything. Okay, and after that, we align the two using the OP. I have experiments showcasing if we do the OP before and after. I will show it in a bit. But over here, for example, is the PPA. So we apply the clustering on the features and then apply the alignment. Okay, and yeah,
BPA looked at everything not independently, but without any class labels, right?
yeah, it's unsupervised.
OP separates the images from the text and matches them and aligns them.
Yeah, so I was just about to explain this.
Okay.
BPA is, you know, an unsupervised transform. We project it onto the, let's say, the yellow features, and then in order to do the OP transform, like, is it a transform? Yeah, I think it's a transform. I can say it's a transform. We need representatives from the two modalities. Okay, so that's where the whoever asked me why is not zero shot, because that's why. I think we had right. Yes. So that's why, because we need representatives from the image domain and the text domain, and we do the alignment based on those representatives. And our classification task is assigning the queries to the text. Okay, so you can think of it as a zero shot problem, but with the supports in order to do the alignment. Okay, yeah.
That's good.
Why is it better?
Yeah, it's like plus, it's not a zero shot problem.
Why?
So what I like to think of it, like my intuitive approach, is if we apply the clustering before the OP, okay, this this gives me a stronger representation in the like it gives me a stronger clustering. Therefore, all of this cluster should be semantically aligned to the same text prototype. Okay. Whereas if I do the OP before, maybe like the intra, think about it like that. If I do the OP before the BPA, all of the distances become like noisier than they were before. And then applying clustering on that shouldn't work as well as it did if I do it after. Okay.
What was asked before? I'm still confused. The stars, how are they computed? So they read
The stars over here are the texts.
only from the text. It's the mean of the text embeddings.
It's not mean. It's basically okay, over here there's a problem. There's like 9 texts, but it shouldn't be 9. It should be 3. Okay. It's 1 text per class.
Ah,
Okay.
so what do you do with the 9 images or the 3? I don't know how many. 3
Okay.
images of that class.
Yeah, so we take the mean of those. That's our representative for like class 1, and the T1 is the representative of the first class of the text, and we have 3 and 3. Okay, because yeah,
But you have for each class you have 2 stars.
no, yes,
And the image one.
yeah, text and the image, and the alignment basically like aligns the two modalities together. But then we throw away the supports. We don't use them. We classify just based on the text, on the newly transformed or the newly aligned text embeddings.
But the alignment is after you compute the average of the images.
The alignment is after I compute the average. Yeah, of course.
So the yellow bar should be smaller here, right? Should be less entries in the yellow one, right? Than the blue. Or not yellow.
I mean,
between the yellow and the red one, it should become smaller.
between the yellow and like the last one.
So the OP, it's not all the yellows, the parameters, but the OP is applied to everything. Like
Yeah, the OP is applied to everything. It's
It's like on the means, but if you apply it on each point separately.
Like you calculate R
The mapping.
based on fewer, but then you apply R to it.
Mhm.
No, you have to, the mapping is, you have 1 T per class.
Yeah,
You want to map 1 S per class.
No, the average S's.
the average S's.
Yeah,
Yeah.
the average S, so 1,
Then if
Right.
you compute the mapping, then you apply the mapping to every
Every single feature.
query,
Yeah.
It's a question if the figure shows that what are the parameters that determine the OP or what are the
output.
ones the OP is applied to.
yes, the second.
So
It's the entire
yeah,
output. It's the entire output. Okay. So over here, since we have 3 classes, then it should be like we use S1, S2, S3 to get the first prototype, then the other 3 to get the second, and then the last 3 to get the third. and we align them. It's not T1 to T9, okay? It's T1 to T3. So it's like this is the pair, like P1 and T1, P2 and T2, P3 and T3. Compute the alignment, and then we classify the queries based on the newly aligned query embeddings to the texts. Okay? Okay.
This is another like a little jump you did there, that typically the text is described in single image, and here they're describing the class. The.
Yeah, but that's input he said in the beginning.
Yeah, it's like a photo of an object, you know. This is like the sentence. It's a photo of a dog, a photo of an airplane. Mhm.
You're basically labeling a query.
Mhm.
And the point,
Okay.
that's the reason you take the average of the images. It's like you think about them as a cluster and you try to get the center of the cluster.
So this is an example of the alignment, for example, on a 2D projection. So if I apply the OP alignment on the raw clip text, on the raw clip features, and versus the BPA transformed features. For my eye, it's easier to see that the BPA features are projected or are transformed better than the raw clip features. If you can see the what it's called, the pink and the red, okay, the blue as well. The purple is like the same, almost the same, but you know, we can see that the BPA is once the BPA has transformed the features, then the alignment becomes better. So you can think of the dots, like the circular dots, as an image representative, and the stars are like the text, or vice versa, and that's our alignment. Like the
And this is a TC that you did after,
yeah.
that's still pretty bad.
I mean, why?
Why is it still?
Yeah.
No, you could see the BPA brought the same classes together, right?
Yeah,
So
like
the reds go together, goes.
applying BPA before the OP actually gives us a better. That's what I meant a lot by clustering before. Okay. Yeah. Yeah, it's I played with this for quite a while, but then once I saw this paper of the double ellipsoid geometry, it's just like fell to me. This is the problem that we need to solve.
Citations that we saw on this same topic from a Stanford group that showed the separation between the 2.
Mhm.
But like not to like this is a point for a plugin. But when we do protein sequence and protein structure modality, we don't get this
Alignment.
this separation. No, ours are
You don't
well
get
aligned. Like
aligned.
the sequence and structure of proteins, they have some many to many relationship, but it's not this bad apparently. And we get it well aligned. So
Mhm.
maybe if someone cares about this.
So the top figure is an alignment like just on a sphere, but this is an interesting figure. Like I really like it. This this basically presents the self-pairwise similarities in the set. Okay, so the rock clip features on the left-hand side, if you can see, like there's a little green dotted line. Gigi, that's your question from before. This separated, we can think of each row as the similarity to the other. Okay, so over here, the ordering is class 1, then class 2, and like supports for class 1, supports for class 2, supports for class 3, for class 4, for class 5, and then query set for class 1, query set for class 2, query set for class 3, query set for class 4, query set for class 5. And then those little like features at the bottom, those are the text. Okay, so what can we infer from this? It's no, it's there's a it doesn't look very good from here, but there's a yellow dotted line that separates the big square from the
Tiny one.
tiny one at the bottom right. Okay? Yeah, the very last five.
It's the yellow piece or the.
Yeah, there's a no, there's a yellow dotted line separating, and then these light hues, they denote like the large modality gap between the text to the images. Okay, and then at the end, there's like these very close intraclass similarities between the text. There's like this small square at the bottom. Okay, so this is very important to understand. Okay, look at the supports, and this square at the top left, this is like a square. Okay, this is a 25 by 25 square. You can see that the supports for class one, like there's the small 5 by 5 square, these are very clustered together. Okay, then if you go down the diagonal, each support is clustered together, but the distances between the support and the other supports is further away. Okay, and then after that we get like this big rectangle, and this is basically the distance between the supports and the queries. So there are also like these small rectangles which showcase that the supports to the queries of the same class are also like very good, but the distances to the others is like a bit further. But the nice thing to look at over here is look at the modality gap. You can clearly see that the distances, like the self-pairwise distance matrix, has these light hues denoting that the image and the text embeddings are much further away, or the similarities. And what happens after we do a BPA transform on this matrix? You can see that the clustering becomes much more sufficient. You can clearly see the clustering over here. And also take a look at the modality gap. It becomes a bit better. But once we do the OP alignment on the right side, you can see that the alignment has been closed, okay? So it collapsed. And I can't zoom in right now, but like when when is the classification good, basically over here? If we see the same hard, like dark hues on the same entries as the support images, okay? Yeah, the rectangles or like the small squares, which we do see it like that over here. Okay. Thank you. Okay, so that's regarding the method. I'm just gonna go through the results real quick. So our experiments were done. If you recall, I said that future classification has this nice, has this thing where the test classes should be unseen by the model. Okay, but unfortunately, when we're talking about foundational models, it has seen everything. Okay, so there are these 10 fine-grained classification data, if future classification data sets, which are supposedly out of the distribution of the training data of Dino and Clip, which is not so. I don't believe that all of them are based on the results that you got per data set, but that's what everyone uses. Okay, and the results at the end are averaged. Like if I use like one shot, then the result that you see at one shot is averaged throughout all of the data sets. Okay, so I just gonna say this right now. For example, flowers has a very high accuracy. Yeah, pets has a very high accuracy. Cars, we got amazing results at cars. Okay, I'm just gonna say the improvement was very good. In Eurosat, like these are satellite images. We also got like some nice results over there. But one of the harder data sets is FGVC aircraft. This is still a pretty, like, this is a hard data set. Okay, unfortunately, even large encoders have a hard time encoding different types of aircraft. So
Question,
Yeah.
so the aircrafts is like one class or within it, there are several classes
Okay, so
inside the,
for example, you can have one class should be Boeing 737.
okay,
Okay,
so.
and the
yeah.
other is,
So it's
I don't know, private jet. Yeah. The same thing for Stanford cars. Okay, so the argument over here is that even though Dino has saw a lot of cars, it has a hard time distinguishing between Ford Focus or Toyota Corolla or whatever. Okay, so these are the results basically. These are on all of the Dino V2 backbones. Over here we have, this is still comparison with us within ourselves, let's say. Okay, so if we take the frozen encoder, I'm just focusing on Dino B right now, since all of them have the same trend. The black line is the regular prototypical, this is classic few-shot classification. We have to go back now to classical few-shot classification, where we take, for example, one shot, and we classify the queries based on that single support set. If we take two shots, then we take the mean of those, 4 shot, 8 shot, 16, and so forth. So at the low shot regimes, BPA, a single BPA transform greatly enhances. But as our number of shots go further up, we actually need this this MLP or this adapter with us to greatly enhance the like the performance. And the intuition for that is very simple. Since we have more supports, since we have more support samples, our adapter learns more during the fine-tuning process. Okay, and yeah, basically. Any questions? Okay. So over here we have comparisons with other transductive methods. Some of these are very recent actually. And still we can see that the single BPA transform has very good performance on low shot regimes, and on higher shot regimes, our fine-tuned adapter method has the state of the art for now. Okay. Proto LP is a nice algorithm. It solves an assignment. It solves an assignment problem using optimal transport as well, and it models the set as a graph, and it does soft assignment on those samples. So for now, sorry, over here, a single BPA transform was a sort of plug and play on the prototypical algorithm. So I did that with other types of what do you call it? Like classifier heads. A linear probe model is basically fitting fitting a linear classifier on using the support set. You just learn a single linear what do you call it? Linear layer. Okay, and we can see that plugging in the BPA before you learn this linear layer, like it enhances the performance. Okay, and I also did some experience over here using the closed form ridge regression classifier. So a feature transform, once we transform the features using the BPA, it greatly enhanced both of the classifiers. So it's not just metric-based learning stuff, but it's easier to do that on metric learning since it's non-learnable. Okay, and it's very fast. And over here, we also tried plugging in BPA into other transductive pipelines. So for example, Laplace shot paddle, Proto-LP, and ECPE. And okay, plugging in the BPA before the classification algorithm, like just transforming the features before, it greatly enhanced the performance there as well. Okay, so these are recent for transductive methods. Going to the multimodal results, these are basically with and without the OP. Zero shot is the mean zero shot across all data sets. And over here we have like just, oh, this should answer Hagit's question. Um, so I have over here like just the raw clip features with the OP transform, and then we have BPA before OP and BPA after OP. And my intuition for that was correct. Clustering before doing the OP transform yielded the best results. And we need at least 2 shots with the late OP transform in order to pass the 0-shot classification accuracy. Okay.
All the previous results were without OP? With
The previous results are not really relevant to the OP because this is just image based. Okay, we only need OP once we concatenate the texts. Okay, so these are.
results with text and without text on the same data set there's a great improvement.
It's not really apples to apples comparison.
You can have something that has text but not use the text. The text helps you.
Yeah, like only using the clip visual encoder. Yeah, I tried that. They vary a bit. Like Dino is more powerful, of course, but yeah, I have some pretty insights. It's not in the slide, but I tried it. I can tell you all about it later. Okay. So yeah, I'm just gonna skip that because that's basically all of it. And over here, there's a nice library which integrated transductive pipelines into text-based feature classification. And on average, we got the state-of-the-art results across all of the 10 data sets. This is on one-shot settings. And our method actually works pretty good on the low-shot regimes. And yeah, hard EM Dirkly and EM Dirkly is like 2025, I think. This is what's the recent state of the art. And we passed that. Also, side note, I haven't put that here, but we are also much faster, okay? Because the BPA can be parallelized on the GPU as well as the OP, whereas they have some other stuff going on. So we are actually much faster.
You can parallelize roughly.
I mean, yeah, it's SVD. You can use PyTorch to do that. So regarding the multi-BPA adapters, as I said before, actually plugging in the multi-BPA adapters on the foundation models didn't yield much greater results, but on the weaker models, it kind of did. So over here, I tested it on 2 different modalities. So for mini ImageNet on the ResNet 12 CNN, as you can see, we got like substantial improvement even with like even with an extra module. Okay, so it converged somehow with three stacks, so 4 BPAs overall. I think it's 4 BPA. Yeah, 4 BPAs overall. And in the audio domain, it also helped over there. So ESC50 is also a nice data set to do future classification on using the audio. There's a nice library over there. And like, look at the improvement. Even just adding a single BPA transform, this is a very weak modality, so BPA really helped over there. And once we added another adapter, it improved there as well, especially in the low shot regimes. Yeah.
Makes sense to use the OP several times.
OP, no, there's no OP here. This is a classic few shot. There's no text.
The text domain, visual text domain, does it make sense to do the OP several times?
So no, none of these methods used OP. They model it differently. They model it like using entropy and other types of distributions. That's what I understand. Really. Okay. Like side note, BPA over here, it's a geometric. I like to think of it as a geometric based approach. Okay, whereas all of the others, like especially the Hardy and Dirkly and the other ones, they are very like statistical approaches. Like they use the entropy and the distributions and stuff. So I think we should end here now because this is not very relevant to the case. Okay? So any questions?
Very nice.
Thank you.
مش ملاقات الكود.